I am introducing Scott Gould from the Claremont, McKenna, Pitzer, Scripps colleges, and he's going
Yep.
to present undergraduate student-initiated and design ODE-based projects using Maple.
Yes, thank you. Thank you for that. Actually, this has been a very good conference. I've gotten lots of good ideas. And the other thing about this conference is it allows me to question what I've been doing and reaffirm what I'm doing. So let's see if my philosophy aligns with many of your philosophies, because most of you people are mathematicians who teach calculus and ODEs, and I'm a physicist, which is probably why the attendance is so low. Okay, let me share my screen. All right, screen numero uno. So there we go. Hopefully you can see that. Are we okay, Anna? Are we all set?
All good.
Oh, good. Okay, yeah. So I actually have an unusual appointment. I am a professor at three of the Claremont colleges, which are small private liberal arts colleges nestled in the foothills of the San Bernardino Mountains, and yes, we were near the fires, but we were in no danger whatsoever. And of course, right now we're into mudslide season. We had almost over 100 millimeters of rain yesterday. Okay, so what I'm doing is I teach an upper division course called Computational Physics and Engineering. And this is primarily for physics majors and what we call 3-2 pre-engineering majors. So they do 3 years at our liberal arts colleges, and then they transfer to a dedicated engineering school. Also, we have applied math majors. The requirements are the fact that they have at least have had a semester, or well, a year's worth of physics. Although I'm actually cutting it back because, and you'll see why towards the end. The hope was that someone was going to give me some suggestions about what I should be teaching in this course, but this is what I thought we should. Historically, physicists have had an upper division math methods for physicists course. It was all done by hand, and the amount of content you're going to see is astonishingly large. So I figured I would do this, but the key is, of course, what we want to do is we want to minimize the amount of time that we're doing algebra and maximize the amount of time when we talk about the mathematical concepts and principles that we need in these upper division physics and engineering courses. So we use a computer algebra system, and as I said, we are using Maple. Uh, of course, the other thing is this is not to assume that we only do algebraic solutions, but we also learn techniques to solve common math problems numerically. Okay, the big three principles of this course is visualization, optimization, and presentation. I want people to come out of this course being able to write papers, manuscripts, so that they can explain to others what's going on, solve the problems, find the maximum outcomes or the minimum of whatever is necessary, and present it well. The topics are, we start with how to become familiar with using Maple, using topics that we are already, the students are already well aware of. That is pre-calculus topics, complex numbers, and single variable calculus. You'd be surprised. We go over calculus, all of calculus, probably in about 1 hour. Then, of course, we jump into ODEs, which is kind of good here. And primarily, we start with initial value problems. These are the issues. I value what the students need to solve, obtain a closed form solution in ODEs is to guess a solution. I would rather them look at it and be able to have some sense of where we're going before we get the computer to solve it. Of course, we will use at some point what was called the slope, the midpoint. These are probably what you people call is Euler or Runge-Kutta methods, but we tend to try not to use certain names in our profession. Of course, we have the big thing is the expectations of the outcomes computationally. And of course, what we want to do is be able to apply this to physical systems. And yes, we do a fair amount of user-generated ODEs, i.e. the modeling that much of this conference is discussing. So I've been grabbing all sorts of good ideas from you people here. So again, I'm glad I'm at this conference. Unfortunately, the rest of the course still has to contain all these items: linear algebra through eigenvalues, boundary value problems, orthogonal polynomials, and all the way through vector calculus. So as you see, at most I can probably dedicate is about 4 weeks to ODEs. How do I get through all of ODEs, and particularly emphasis on linked sets of differential equations? Is because I try to get the computer to do all the problem solving. We spend more of the time of setting up and understanding what we get in the outcome. The big thing advantage of using Maple is it allows me to emphasize concepts, concepts, and concepts. Maple, and particularly, has a low barrier to generate content. Maple math, it looks like textbook math. It is a physics principles first approach. Most computational models is you have to start from the bottom up. You define B before you can use B. Well, and essentially that's not the case here, and we'll show some examples. Physicists use top-down thinking, and we would hope that also engineers do as well. So Maple allows us to do this. Again, the principles that we are trying to discuss are not done through mathematics, are done through mathematics and not through a black box. The big deal is we want to eliminate paperwork minutia and teaching tricks. My goal is not to use tricks. Sometimes we have to think about other ways to solve a problem, but I don't want them to say that this course consists of learning certain procedures. Solutions are symbolic. What this does is this allows us to look at a solution and say, oh, how does the mass affect our system, rather than having to rerun the problem several times to see how a mass might affect our solution. In addition, it allows us to, of course, solve beyond the spherical cow type model problem. And we try to really emphasize, I try to emphasize minimal amount of coding. So essentially those 4 commands are about all I need them to do. They eventually learn more, and that's the goal. That's great, but I don't really need much more than 4 commands. And of course, the idea is these should be transferable skills and principles. So let's look at a quick example. This is a classic example of, we'll just but in 2 dimensions, of a mass on a spring. So the force of the spring is along the direction of the mass. We'll assume the top here, up here, is going to be at the 0, 0 point, and this mass is moving from here. And of course, we'll have some gravity, which is purely in the vertical or y direction. Let's see if I can get this to work. Look at that. There it is. And this is what Maple looks like. Many of you might have been talking about using Jupyter notebooks. Maple and Mathematica have been notebook-based for, I hate to say it, I think decades now. The big deal is, again, we can start with the first principle, and I can write this in a vector format, that the rate of change of momentum is equal to the net force. This is the momentum principle, or what you probably, again, call the Newton's second law of motion. Well, what does P as a vector mean? That means it's a vector with an x component or y component. What is the force in our particular situation? It is a spring force minus k times the displacement, plus m times g. What is this displacement? Again, that's a vector with an x and y component. What's g? G is also a vector with a 0 in x and minus g in the y direction. We can then define the second key relationship, is that with the momentum, we can define what a velocity is, and we can provide some initial conditions to our situation. And there, lo and behold, we really only have one procedure that we have to memorize, and that is desolve. If you don't like the solutions, here's one that the students do like to memorize, is simplify with some sort of assumptions, and now your solutions include omega. Okay, let's go back to this one. Moving on. Okay, how do I get this all done? Is because I have built a YouTube website, and on it I have put all sorts of videos. So if you go to the Maple Prof website, and you can see my what's going on here. It includes essentially the first textbook, it's a video textbook, is Learning Maple Fundamentals. Again, these idea is that YouTube is the wave of the future. We're going to get rid of textbooks. In fact, we know that the number one physics textbook now is purchased nearly exclusively virtually. There's the printing of these textbooks. This number one textbook is basically has disappeared. Um, Here's my other textbook, Learning Mathematics Using Maple, going through the content of the course. Again, the nice thing about video is you can treat playlists as textbooks, and I essentially am working towards 4 different textbooks. One particularly will be my grand one, which will be Learning Physics Using Maple. Um, Videos can be viewed as chapters, and we can link them through icons, so you can go forward and backwards in chapters because we want to solve them sequentially. Once they read vectors 1, they want to move on to vectors 2 or something like that. Okay, and the nice thing is I also put some thumbnails in for easy identification of content. How are we doing? Well, are we doing pretty well? All right, so this course goes through all the material, and instead of a final, we have a project. And in the project is basically they only have a week and a half to do the project. And so I have some rubrics, some values that I want from the course. Obviously, it has to be able to do correct physics. If it's not correct physics, we get some problems. It's got to execute. We would like to see some animation. We would like to see something that is presentable so that we can actually go on and interestingly enough, get some educational value in it. I'd like to be able to present this to other people. Obviously, there needs to be some sort of sophistication and complexity. If they come up with something particularly original, that's great. If they are modifying what something I had prepared for them, that's not as good. These are the rubrics here. All right, so I'm hoping I can go through 4 examples with the remaining 10 minutes. Probably not, but what we'll do is we'll look at the highlights of them. Going back to our image here, here's final project number 1. This project consists of how do I model the having my coffee go over the top of my cup. And the way the model is done is what we're going to do is we're going to have a hand. The hand is going to oscillate. And so this is a forced spring type situation on a pendulum. So this will go back and forth at some periodic frequency, and then the pendulum, which is going to represent the edge of the coffee, will go back and forth. Again, so this particular student, and again, I'm going to show the bad with the good. Some of them kind of make me cringe a little bit, but that's okay. She started with a Lagrangian. She worked through the equations and motions, did all the calculations, and again, had the computer do it. She could do a little of this by hand, but the big deal is when she started to plug some sample values in, she saw that if she chose a frequency that best matched essentially the resonant frequency of the coffee moving in the cup, or essentially the pendulum, she was able to get the pendulum, or really the coffee, to spill over the edge, and that's the story there. This one is not a particular, and then you can sort of see as she can plot how the angle changes time and putting some phase in, et cetera, et cetera. This is a fine project, not one of the better ones. Let's look on something a little more sophisticated. Well, this particular student was going to look at the trajectory of a soccer ball. They did not put spin in, but they did have drag, and they decided to do this in 3 dimensions. So again, what they're going to do is they have a force in the X, Y, and Z directions. And again, it's very easy for them to write out the ODEs. This particular problem will be solved numerically. If we triple exclamation point, we can actually execute the entire program. all at once. There are other plots that go in it, but let's get to the fun part, which is right down here. And so in this particular thing, she'll set up a situation where we can ask what if questions. So v sub 0, 0 is what is the speed of the ball. If we slow the ball down, we find that the ball travels from here into the goal, towards the goal this way, but reaches the goal at a lower height. Oops, than if we push it higher. And of course, if we push it too high, oops, is this going to do this? I may have to do this again. Hang on. If she pushes a velocity too high, yeah, maybe it's not. She's probably matched out. So what we can do is we can look at the angle in the vertical direction. We, as physicists, measure the angle off the z-axis with theta, not phi. So if she pushes it this way, she aims closer to the ground. Theta is pi over 2. She hits it this way. She now pushes the ball with an angle, so initial kick, so that it goes over the net. And what we can do is let's move this back, and she can, of course, vary the angle horizontally to determine whether she's going to hit the ball or not. So again, the nice thing about this is it went through all the differential equations. It makes a nice presentation, and it provides us a situation where we can ask what if questions on our own. The user can. Here's another project. This one particularly, let's see if I can draw the picture. No, there's not the picture. This one is basically a picture of a volleyball, and he wants to know, given a certain amount of spin on it, can he get the volleyball to go over the net, but still land in the court? I will not go through all. This is much more complicated, and this person had way more programming skills, so they ended up writing a fair amount of code. But the fun part, again, is it allows us to set up a situation of a what if. So in the X direction, which is away from the ball is here. And if we click on the ball, and if we change it, oops, actually, you know what I'm going to do? I'm going to stop this. I'm actually going to execute the whole thing. There we go. Let's go to the bottom again. All right. The nice thing about this is if I click, oh, oh, oh dear. Oh dear. Oops. There was animation. All right. Well, that's not going to work. And unfortunately, that did not, I would actually have to reset it. The last one, oh well, these things happen. The last one is this one actually got published in a journal, and it looks at a three-body problem with different masses. So again, the person can present the content just like in a notebook. They used a font I wouldn't use, but whatever, it's still a good idea. Okay, they solved the three-body problem numerically. Here is a trajectory of three equal masses. The fun part, of course, is to click on this. And I'm going to have to do the following. I'm going to switch back to here. And I'm going to close and restart. There we go. You should be able to see this. And let's see, does this work? Yes. The nice thing again, now here is essentially this person has built a fair amount of animation, and it required really only memorizing one command, which was animate. And again, students have a tendency to go hog wild. They want to cure cancel in a 2-week period. And that's really cool. I enjoy that sort of thing. Here's another type of problem. This one is 3 unequal masses. And again, depending upon the initial conditions, the object can move, in a particular direction. This is very useful for us in terms of demonstrating a net momentum in a particular direction. Let's look at one other. This one, what it does is, again, he set this up so that you can change. Oops, we're not going to do that because I have to run the whole thing. Let's not do this. This one is particularly kind of fun. We end up with a solution. Why? Because we end up with a situation where we have a very stable solution for the three bodies. And when they do this periodic type motion, or let's go one more. No, let's not do that one. Yeah, what the heck? Let's do this one. And eventually, he also did a three-body situation of two masses. And then he actually can look and demonstrate how the sun oscillates as the masses move around the sun. So those are some of the examples that we did here. There are other examples. So my conclusion with the rest of it is a lot of what I needed to do to make this course better was to talk to my colleagues and ask them, what do you value in your courses? What principles do you want them to see? We didn't talk about solving these things, eigenvalues, but we certainly covered that. And the other thing, of course, is question everything you teach. Don't assume that just because that's the way you were taught, that must be the true answer. It's astonishing how many of our younger colleagues still have that attitude. I was hoping they would continue be more progressive, but it's interesting. In our environment, maybe not at your colleges, but in a lot of colleges, we are actually assessed not on ingenuity in our education, we are assessed on ingenuity in our research, essentially. And yet, what we want is we want students to be experimentalists, to try different things, to be willing to fail. And it makes it harder for our younger colleagues who are trying to get tenure to try anything new because it may fail. But I hope that once they do, they can, again, question everything they teach, and that's what I do. So with that, I think I am done.
That was wonderful. Thank you so much.